session. We're just looking for panelists, but please take your seats. Okay, we have the panelists. We need you to take your seats. We're going to start the panel on what tools are critical for making progress in cosmology in the coming decades. So this is a slightly different panel. We're not harping on a controversy, although maybe it's contentious what we should do. And we're dealing with experiments and tools as we go forward. So we've learned, of course, we're here to learn about cosmology and cosmic controversies. We're thinking of dark matter. We just had a wonderful session on dark matter panel and a session this morning. We're nearing, as what Rocky had dubbed a decade ago, we're nearing the end of the decade of the WIMP. So now we need to plan for the next decades. And we heard in the last session whether or not the WIMP is dead or not depends on how you define the WIMP. But certainly, of those 90 orders of magnitude, there's a lot of room for future exploration. Dark energy, we heard a lot yesterday about do we just keep chasing W? When does it make sense? When is W minus 1 the answer? Plus there are lots of other ways to get at dark energy. We're doing stage 3, we're getting ready for stage 4. What's next? Inflation, of course, wonderful theory. We had a panel on that as well. We're chasing B modes right now, and we're making tremendous progress. It wasn't long ago before the B modes became more sensitive than just measuring the temperature, anisotropy in the CMB, and in a couple of years we'll have an upper limit or detection of R 10 to the minus 2. We are now designing and building stage 4 experiments to get us down to 10 to the minus 3. At least 2 are look like they're approved to do that. What do we do if we don't see it then? What are other ways? Will the 21 centimeter mapping of the dark ages get us there? Are there other methods? What's the future there? We've been concentrating a lot on controversies, anomalies. Are they hints of new physics? Are they systematics? Are the anomalies also hints of physics or just statistical flukes? And of course, what we all want to do is stress test lambda CDM. We'd like to see it break. We'd also like to know what is the physics behind the components of lambda CDM. So what are the tools for going forward? And that's what this panel is about. It's a very broad subject, and we don't have infinite resources and money. But if you look at all the things that are going on, and let me tell you, this is, there's no thought went into this ahead of time, just names written down there, although I was very happy to see CMB polarization came out right in the middle, as it should. Multi-messenger, what came up in the last session, but yes, that's going to have a role. There's lots and lots of things. Each one of these things, and plus I'm sure I've left out many, has many experiments behind it. So it's very complex, and if we had a bunch of experimentalists up here, they would talk about one idea why it was great, and they might be bounded by thinking about what's actually possible to do. So we have this complex landscape, all these things to do. How do we make progress? So we decided to ask theorists about this. So we have Jonathan Fang. I think we'll probably concentrate mainly on dark matter. Rashid Sanyaev, we'll find out on what. And Roger, who I'm sure can tell us a lot about a lot of different things. So we're going to get started right away then with Jonathan. Does your mic work?
Hello? Hello?
Nope.
Can you hear me?
Can you hear Jonathan?
Hello?
Pick up. It's on.
That don't talk for sure. Okay. Okay, it's a great pleasure to be here to talk about this and to join this panel. This is got to be one of the most broad questions you could ever ask a panel. my translation of the question is basically, what's interesting? And so I'll try to answer that. But we have split it up into different topics. As you've heard, Roger has generously agreed to cover everything that's not covered before he talks, so that'll be great. So I'm going to talk about dark matter. So we just heard a panel talk about dark matter, and I did not realize that they were going to talk so much about some of the things I'm going to talk about. You might think that we should have realized that, given that Tim is about 5 meters away from me in terms of office doors. But he's gone to the dark side, not the cosmological dark side. It's actually, he's become chair. So that has limited our communication on things. And so I actually didn't know that, but there will be a lot of overlap, and hopefully I'll say some things that were not covered, either because I guess they're too uncontroversial and boring, or because people just never have to know. All right, so this question for dark matter is, however, very timely. From a sort of sociological point of view, there are new community exercises underway in both astrophysics and particle physics. So of course, dark matter is a topic that sits right on top of that interface. And so, of course, Astro 2020 is going on. European Strategy for Particle Physics Update just came out with their briefing book. They're supposed to have drafted recommendations in January 2020. And STOMAS 2021 is just starting. Probably more interesting, though, is just from an intellectual point of view. There are many new developments in dark matter. WIMPs and other classic candidates, like the axion, have not been discovered. They remain interesting. Other dark matter candidates are rising in prominence. And both of those facts have real implications for what tools and experiments will be needed for progress, I think. And I'll try to give you my read on some of those implications. Let's start with the WIMP. So for decades, of course, the WIMP paradigm has been dominant, bolstered by the WIMP miracle and its many implications. So this is a plot that I first made in 2008. It still is probably my favorite plot for just overviewing this whole field. I mean, we need to just sit back and appreciate why WIMPs have been so dominant. It's because they have such incredible implications for so many different kinds of experiments. So, of course, you can have WIMPs annihilate. That's indirect detection, and they can go to every particle in the standard model. So neutrinos, you have neutrino telescopes, gamma rays, all sorts of telescopes and observatories, positrons, antiprotons, anything you can think of. So it's an incredible variety of signals. Direct detection, the mass is just magically matched to scattering off a ball nuclei. There's actually no reason that the W mass has to equal the xenon mass, but it does. And that's been exploited to great effect. And then at colliders, almost at this point, every BSM signal can be sort of folded into the dark matter family. All the missing energy signals, certainly, but this possibility of WIMPs has generated a whole industry of mono-X searches. So mono-photon, mono-jet, but now at this point mono-Z, mono-W, mono-top, mono-Higgs, every mono thing in the world is now being searched for. And they all come back, they're all basically searches for dark matter. What is the status of WIMPs? Well, there are certainly many constraints now, but it's definitely still viable. People talked about this in the last panel. I would say I'm much, much more on the positive side. It's absolutely viable, and I'll give you an example. There are SUSY models where you don't have to drop any of the things you liked about SUSY WIMP dark matter, and you still have them viable. So namely, you can impose the thermal relic neutrino constraint. So they have to freeze out with the right relic density. You should make them for natural. Squarks and leptons are below a few DeV. You can keep coupling cost unification, all the little bells and whistles you want, you can keep them all, and still you have a viable theory. As an example, let me give you MSSM4G. That's the MSSM with a vector-like 4th generation. The bottom line, this is really for experts if you want to get into it, but there's a fundamental tension between getting the rod density right, which requires you to have pretty good annihilation, and not having a big enough cross-section that you would have been seen at the direct detection places. And basically this model gets around it. The dark matter is 200 to 700 GeV, it's phenolite, so it scatters very weakly, so it's not excluded by current direct detection bounds. Yet it freezes out because I now have a 4th generation and that allows me to get the right route density. Okay, so there's a nice little plot here where we sort of scanned over all the parameter space. And you see that this is, the neutrino mass on the bottom, the proton cross-section on the y-axis, and all those colors are viable models. And you see it just completely fills in everything from whatever the current bound is now to the neutrino floor. And as I say, this has all the bells and whistles intact. So, that's an existence proof. I think there are many others. And I would say the bottom line here is that there remain strong motivations to pursue direct detection down to the neutrino floor, both in xenon, which has got several flavors on different continents, and in argon. I don't see any reason to stop now. The neutrino floor is not that far away. These experiments are not that expensive in the great scheme of things. And we're talking about a field here where, every 3 years they improve their limits by an order of magnitude. Why would you stop? Okay, so that's one tool or experiment I think should be strongly motivated. Collider searches. For the next many years, the energy frontier will continue to be dominated by the LHC and the high luminosity LHC. The LHC is currently in long shutdown 2, but will start up again in a couple years, 2021, and run through the high luminosity era for another 16 years. And so over here is a plot you see of the luminosity gathered as a function of year. And we are, can you see this? No, you can't. Well, okay, LS2, that's second from the left blue band, that's what we're in right now. And you see that the solid blue contour rises very, very fast as you get to the high luminosity era. And we're nowhere near having got, most of the luminosity from the high luminosity era. So, there's an open question. Will we find new particles through conventional searches, the ones that we've been using so far? People have different views on that. I'm much more optimistic than most probably, because I sort of think that people are smart and all these sort of conventional things that we think about, get improved. Backgrounds get rejected better and smarter. But certainly an obvious question, what other approaches can enhance the prospects for discovering dark matter and other new particles? So in this category, and this is certainly not my field, but I would think that it's an important one to mention. I haven't heard it mentioned much yet here. Machine learning is now able to optimize searches over conventional methods in this collider context I'm talking about. So for example, one of the primary applications of this is to identify the originating quark or gluon from a hadronic shower. So here you see a typical event display where the protons come in, they collide, and out comes this stuff, and now you're supposed to figure out what that was. Some things are easy, like that red thing is I think a muon, but all that orange stuff, what is that? And it's probably hadrons, it's a hadronic shower, but is it a bottom quark or a top quark or a charm quark or a gluon? It's not that obvious. People have, however, started applying machine learning techniques to figure that out. So here's some examples. So on the both plots, on the bottom is the signal efficiency. You're trying to find either B quarks on one side and the top quarks on the other side. And then the y-axis is basically telling you your purity. How well are you doing rejecting all the other junk you didn't want to get? And okay, so there's B quarks on the left, let's say. Okay, so the red contour is how well you do with neural networks, and the black contour is how you do if you're just a really smart person. And you note that the neural networks do better. This is the work of Daniel Whiteson and collaborators, including a number of computer scientists. On the right side is work of Tillman Plain and collaborators, and that's looking for top quarks. And the point is that these neural networks are doing better than one might have expected, and certainly better than people. And you should note also that it's a log scale, so the improvement might not look as dramatic as it is, but it's actually significant in terms of just without it, can double your effective event sample in some cases. So I think that's a tool that certainly will become more and more prevalent as we go on. Okay, axions. I'll just give this short script. This has been discussed at length at this conference. But let me just say that the QCD axion remains a highly motivated dark matter candidate. I mean, it's just incredible. This is probably one of the original dark matter candidates proposed in, what, 76 or something like this, 77. And yet we haven't even probed the heart of the parameter space. We haven't even got anywhere there. Here's a recent plot from the ADMX G2 collaboration. And you see, so the axion mass is of course some window, but sort of the sort of sweet spot is around several micro eV. And you're trying to get into that range sort of at those purple bands or below. And you see just recently, through an incredible amount of work, bounds are now sensitive to things in that range. And so that's great, but there's still room to go. And so certainly this is a place where we have just got on the cusp of actually hitting the interesting region, and we should continue on that. It's not easy. Going to higher and lower masses is well motivated, and that's not as easy as you might hope it would be. But I think that's a classic great motivated candidate. Okay, so those are kind of classic candidates. Of course, the absence of a compelling dark matter signal so far, and in fact, a compelling beyond the standard model signal of any kind so far, motivates the study of other possibilities. So in recent years, there's been a huge growth in the number of dark matter candidates under investigation, and that's been great. More important than just the number of new candidates, I think, is the fact that many of these are amenable to searches by small, cheap, and fast experiments. And so this is really a growth field, and something that I hope something we'll see in the coming decades. So this is a plot that came out of the Cosmic Visions exercise a couple years ago of many different kinds of dark matter candidates. The top row there, you sort of see the standard one, the classic WIM, QCD axion, stellar neutrino. And then, but below it, you see a whole bunch of other ones that have come now to some prominence. And then there's anomalies, and then there's various search techniques. But this range of masses that are interesting has expanded greatly. On the right, you see black holes, primordial black holes, and there's a great talks on 1.1 about that. I think that's very interesting. And then there's an expanded, sort of around the WIMP mass range, there's an expanded region, hidden thermal relics and WIMP-less dark matter. I'll talk more about that. And then there's a huge range going down to the ZeV level of ultralight dark matter. We've also heard a bit about that. So for those who have, get a headache every time they look at a plot like that, let me try to say some of why some of this is interesting. So if you haven't seen anything, what you might want to do is just go back to the drawing board and try to be very, very simple-minded and say, look, we need to find some new particles of some sort. Where would they be? So you would probably make a graph like this. They have some mass, they have some interaction strength, and they're somewhere in this plane, and you go look for them. Particle experiments come in from the upper left corner, and things like the electron are been seen a long time ago, but basically all the standard model particles up at the interaction strength of order 1, and we're moving toward the right. Those things, though, are already discovered, because they're strongly interacting and not so heavy. Then you have stuff that's basically impossible to discover, because it's either heavy or very, very weakly interacting, or both. And then the place where all the action is on this diagonal. You have strongly interacting heavy particles, and you have weakly interacting light particles. And so from a purely particle physics point of view, being very, very much sort of a let's look under the lamppost sort of point of view, this is where you should be. You should be playing the game on that diagonal. Now, the nice thing, though, is that that thing plays very nicely with cosmology. So the possibility that there are particles that are weak and very weakly interacting also has cosmological motivation. So here's this classic, famous thermal freeze-out contour, and you know that WIMPs are beautifully designed to just freeze out with the right relative density. But the relative density actually goes as the mass scale of your new dark matter particle divided by the gauge coupling square, or the mass square of the gauge coupling before the coupling. And so you can actually plot in this plane of mass and coupling where you get the right relative density, thinking of those as free parameters. And of course, WIMPs are on this curve. So around 100 GeV and sort of order 1 coupling, you have WIMP dark matter. It's wonderfully motivated, blah, blah, blah. But the point is that there's this whole other region down here where you also have the right relative density. You just have lighter and more weakly interacting stuff, or possibly even heavier and more strongly interacting stuff. And so Jason Kumar and I call this the Wimpless miracle long ago. Many other people have also talked about this. And it's just a simple fact that this sort of WIMP miracle doesn't necessarily point to 100 GeV stuff. It could actually be much lighter and more weakly interacting stuff. So we like to call it the WIMP sector, but it's also hidden sector dark matter, secluded dark matter, blah, blah, blah. So there are lots of things in there. And so the bottom line is that, here's the particle physics landscape, but there's also a cosmological landscape. Up here, those were already discovered, but that didn't matter because there was too little of that to be dark matter anyway. Down there, impossible to discover, but that's okay because that didn't make up any of the dark matter anyway. And right on this diagonal is where all the action is cosmologically. It's just right to be the dark matter. So this lining up of the cosmological motivation with the sort of particle physics where could you find anything anyway diagonal is, I think, very significant. Where could you get these light weakly interacting particles? Well, they naturally emerge from generalizing dark matter to dark sectors. So the story here is, suppose that you have a standard model with all of our fields, including our usual photon. But suppose you have another sector, dark sector with dark matter, but maybe it's also got other stuff in it, like the U1 gauge force. Turns out then that you can ask how do these two sectors interact with each other. And there's one operator you can write down, which is dimension 4, which is F mu nu dark. And that will be generated by any particle which has both standard model charge and dark sector charge through a loop there with some particle with mass m. And this is something that goes way back to Bob Hold'em. And if you go through and analyze this, what you'll find is the prediction of a model like this is that you have a weakly interacting particle. It's weakly interacting because that loop is a loop, and so the mixing is loop suppressed. But you have a very natural reason to think that there should be a particle popping out which has 10 to the minus 3 or 10 to the minus 6 or some sort of suppressed coupling. And that thing is actually now called the dark photon. And so this gives another way to sort of get to that story of light weakly interacting particles. And I want to just point out that now we're looking not just for dark matter, but also for dark mediators, which are not the dark matter. There are other possibilities, dark photon, dark scalar, dark fermion. But this is where they all come from. There's some very, very simple setup like this, and they all just pop out. Okay, so that was like a theoretical interlude, but then what does this have to do with tools and things ways forward? If you have a possibility of a dark sector sitting over there like that, it allows quite naturally for the dark matter to be strongly self-interacting. It's even more motivated by the idea that this stuff over there ought to be light for the reasons we just talked about, say in the MeV to GeV scale. Think 10, 15 years ago, someone told you need a dark matter interaction at a barn over a GeV scale, or a centimeter squared scale. You'd think that's just so weird and exotic, no one would believe you. But here, you have a dark sector. Why couldn't it have very similar interaction cross-sections to nuclear matter? In fact, that's probably the most natural thing. You put QCD in a dark sector, you're going to get QCD-like interactions. So from this point of view, it's very natural for dark matter to have non-CCDM properties. And to try to put it in the context of this cause of controversies, there was, of course, a panel before, which was, is a theory beyond cold dark matter needed to describe structure formation? And I would say that's a little old school at this point. The new question that really should be asked is, what can structure formation tell us about dark matter's self-interactions and other properties? It's not as biased toward cold dark matter. That isn't like the default anymore. There's a whole range, and it'd be very interesting to know what structure information can tell us about these self-interactions, especially in the absence of sort of particle data. So I think there's very strong motivation for n-body simulations, other ways of pulling small-scale structure. All these things now are, there's a continuum now. It's not a yes or no sort of thing anymore. And I would hope that would also be very big part of the coming decades. Okay, light weakly interacting particles put premium on new ideas because, as we'll find out, they don't require enormous investments. Put a premium on new ideas, new techniques, and have really engendered a lot of new collaborations between theorists and experimentalists. There are many new ideas in indirect detection and direct detection, as we've seen earlier in the morning and also in the earlier panel, and both for existing dark matter detectors and in proposed experiments. So you can actually repurpose like a xenon 1 ton and get really interesting data out of that, or you can also propose brand new experiments, and these were discussed at some length. There are also, however, new ideas for collider and accelerator experiments, probing these light weakly interacting particles, and also long-lived particles. And so at this point, I will, let me just tell you that this is a subject of great interest. There have been working groups in various continents looking at this. This is a report of the Physics Beyond Colliders group at CERN, which outlined various ways that CERN can make progress looking for new physics besides the sort of standard places. And there's a whole variety of experiments with a variety of targets and also a variety of timelines. So worth noting that here in this circle are a bunch of experiments who have very short timelines. And so we're not talking about, LHC 30 years in the future sort of things. We're talking about stuff that can be done like next year or the year after that. And so at this point, I will now remove my theorist hat and put on my phaser co-spokesperson hat and completely shed all pretense of being unbiased and just talk about phaser, okay? Because that's what So, new physics at the LHC is focused on high PT. This is appropriate for strong interacting heavy particles like a gluino or a squark. However, if new particles are light and weakly interacting, and I'm trying to give you many reasons why that's a good thing to think about, the way detectors at the LHC have been designed and may have been completely misguided. The reason is that if you have light and weakly interacting particles, you can produce them in meson decay, like pions, extremely light standard amount of particles. And they are typically produced along the beamline, where the detectors have a blind spot. So here you have the Atlas detector, the protons come in like this, and what I'm telling you is that you have a dark photon. The dark photons will be produced and go out in the same direction the photons came in. So exactly the place where you have the least coverage is exactly the place those things preferentially go out. And so you can enhance the LHC's discovery reach by putting a detector where all the pions are, namely down along that beamline. Now, if you put it right on the beamline, obviously you're going to cut off the beam, and that will not be a good thing. So you'll get no interactions at all, so that's not a good idea. So what you need to do is walk down that beamline straight, really straight, until you find a place where the beam is curved, and then you can put your detector there, and you will see all those dark photons that really do go straight show up in your detector. And so this is what phaser is, or at least where phaser is. So you go down Atlas about 480 meters, and it turns out there's a little tunnel that was previously unused and occupied since the days of Lepp, which is actually exactly on the beamline, except for the fact that the beamline's curved, right? So things that come straight out of the IP will go into that little tunnel. So on the bottom, you see the view looking west. This thing over here is the LHC beamline where all the protons are, and this thing here is actually a new tunnel where all the new particles would come out, dark photons, dark Higgs, xenon, ELF, stuff like that. And that's the dark sector. So we have started building a collaboration and a detector to do this. This is the recent form of this detector. I won't describe all the details except to say that the entire thing is about 5 meters long. So the active decay volume is 1.5 meters, so that big, and about a cross-section of a sheet of paper. And it has a total volume, including all the magnets and everything, of 5 meters by 1 meter by 1 meter, but it's basically a tabletop experiment. It could sit on this table here. That experiment has now been approved and funded in March of this year, and by CERN and Heisey Simons and Simons Foundations. Is now under construction with very helpful contributions from LICB and the Atlas SCT collaborations. And Okay, so there's a little bit of missing stuff here, but basically the point of these plots is because we're looking at a completely new way, we will be able to start probing new parameter space with the first inverse femtobarn of data from the LHC when it starts again in 2020. And so you know that the LHC is planning to take about 150 inverse femtobarns in the next 2 years. So we're talking like the first week of data or so. And possible upgrades will improve the sensitivity by a factor of about 1 million. So this is the collaboration, the number of executions involved. These are some fit photos from the site. We cleaned it all out and it looks very nice, it's ready to go. This is a tracking layer that we've just very proudly assembled just last week. And we combined a couple of these, 3 of these to make a tracking station, 3 tracking stations to make phaser. And that's by the hardest part. And so last slide, let me just say that this is obviously something that's near and dear to my heart, phaser, but I introduce it here because this is an example of something that can be done quickly, right? I mean, this is going from theory paper to data in about 3 years. Cheaply, it's very small. There are other ideas on the market. Just here are a couple other than CERN, but there are others in other laboratories around. And so this is a really exciting and new era where we're not talking about billion-dollar, 3,000-person collaborations. We're talking about fast, cheap, and small. Thank you.
Okay, well, next we have Rashid. So I say even theorists have their experiments now.
Do you hear me?
No.
Okay. No?
Okay.
Well, they want to
Yes.
answer.
Yes.
The
Yes.
answer is obviously yes.
Yes, okay. And is it possible to get pointer? No? Okay, here. That is good. Yes, excellent. Yes. Yes, I will tell you about maybe one of the biggest dramas in my life. This was the old concept of the spacecraft, spectrum RG, spectrum with gamma, which we started in '87, and a lot of great physicists like Zeldovich, Sakharov, Sardeev, they're helping us to get permission from Brezhnev and then Gorbachev government to organize very broad cooperation with UK, with USA, UK, Denmark, Italy, Israel, Germany, Turkey, many countries. Everything was possible. I can tell you that bulk spacecraft was practically finished. A lot of devices were produced. This device, JETX, Joint European X-ray Telescope, is working already maybe 10 years on the Gerald Swift spacecraft, American, just its spare model. But this project was closed in the last moment in 2001, and drama was very simple. There were great changes in the Soviet Union, and the mission was delayed and then canceled, and then many devices were ready to fly. I remember how chief of the Russian Space Agency, I don't know why, but he was very supportive to this mission. He told me, Rashid, I cannot do anything. country is twice smaller, population is twice smaller, budget is twice smaller, and your spacecraft also should be twice smaller. And I asked, is it possible? He told, yes, just start to twice smaller. It was impossible in reality to adapt all devices. They were very big to the smaller spacecraft and smaller rocket at that time. Finally, we decided to change completely the strategy, and instead of this Christmas tree, we decided to go to much simpler instruments. I should play here. And this is a spacecraft, new, only 2 instruments. This is in Lavochkin industry near Moscow. And I can tell you it's still rather huge. These are not specially grown dwarfs, but these are people who are younger than I and even taller. You see that, and this is a Russian device, Arctic Sea. It is produced by Institute of Space Research in Moscow and Russian nuclear, Federal Nuclear Center in Sarov, where Zeldovich and Sakharov were creating different dirty bombs, let's say so. And this is a spacecraft produced fully by Lavochkin Association, and this is Rosita, German device. The history is simple. When we came to the idea of this spacecraft, we decided that cosmology should be part. And at that time, I was really shocked when we understood that there is final and not very big amount of clusters of galaxies in our universe. Only 100,000 of objects with masses higher than 3 times 10 to the power 14 solar masses. And this was so interesting, and also practically afterwards I saw how the computations of Virga, Volker Springel, and Simon White is here. We understood that every cluster of galaxies is in the nodes of the cosmic web. And therefore it's very interesting to observe them and to get very big sample. We were discussing with many people. Günther Hasinger, who is now the scientific director of European Space Agency, was very interested, but he told that Germany can produce only instrument which is able during sky survey to observe maybe 2,000 or 3,000 clusters. I told no. I was sure that people who are in microwave will do this earlier. I told no, 100 or nothing. Finally, we came with the concept of Rosita, which is in reality 7 telescopes here. Then Russian device immediately also organized a cluster of 7 telescopes. I can show you, this is the start. It again was the same rocket which we planned for the old Spectrum X. It is proton, 3-stage proton, and then 4th stage was enormously powerful booster which was not necessary for us, and it was created to deliver in the 60s and beginning of 70s to deliver people to the moon. And this everything worked perfectly. I have movies how it went. This territory of Kazakhstan, now independent state, former huge military base also, and the place from where a lot of Russian astronauts were going to space. Launch was really beautiful and going the wrong direction. Orbit we choose L2, and this is first X-ray spacecraft which is already close to L2. Spacecraft now today, I think it is at the distance 1,630,000 kilometers away from the Earth. It is in reality already satellite of our sun. This is picture from our institute, Space Research Institute, but Predel and Robreit from Hamburg, still they made this movie so that you see how orbit is evolving, and it's quasi-stable orbit. In the end of November, we will make maybe a little earlier, there will be final, how to say, ignition of the spacecraft engines, and it will go to the orbit, which will be stable at least half a year. Its orbit is practically similar to Gaia orbit today. Let's move further. I should be faster. These are 7 flight mirrors of Rosita, but naked, without all protection again to walk in the space. And there are we are very happy. There are magnets, obviously not how to say, just current is going, and it doesn't involve, permit the low energy particles to be focused to the detector. This is a Russian device, Pavlinsky SPI. It's yes, and also 7 detectors. And what is the important thing for people who are doing AGNs? This might be why it is. Could you tell me why it is not showing? Check please. This yours. But I can tell you that there is a very important thing that at the bottom you can see the. Oh, yes. Okay. Thank you, Roger. It's afraid of the host. Yes, this is the Rosita response. It is the maximum maximum sensitivity, maximum surface area is between 0.5 and practically 1.5 or 2 keVs. And then drop. This is just the property of the X-ray mirrors. And hard X-ray instrument, which mirrors for it were supplied by Marshall. We have in Russia our mirrors, but Marshall's mirror are a little better. Therefore, we got permission to use them, and you see that the device is sensitive in 530 keV, and from the beginning, main goal for this device was to get sample of Compton-thick AGNs and galactic hard X-ray sources. I will show you pictures. These are 7 detectors of Arctic Sea, and all from the beginning are working very well. This image of the center of our galaxy and diffuse emission here. This is the Thomson reflection of flare of the Sagittarius A star 100 or 150 years ago. And details on this picture of scattering are moving with a little subluminal velocity. We see how new region, another molecular cloud appears every 3-5 years, and how this radiation disappears. And this is comparison with well-known spacecraft of Fiona Harrison, she's PI of the Noob star, and Caltech and Columbia were responsible for its creation. And you see this is mosaic, center of our galaxy, and time to get this mosaic is 144 kiloseconds, a lot of time. And this is Arctic Sea, 4.8 kiloseconds, less than 1.5 hours, and you see all the details and also this scattered gas, and angular resolution is a little better. And what was also important that in this image, Sagittarius A star was extremely bright. Here it was a little fainter. But Arctic Sea nevertheless detected it when Sagittarius A star was 75 times brighter than its usual brightness. Now I will show you image of one of 7 detectors of Rosita. I like this image. It is field, well-known field depth, 2 to 2 degrees. You see it. And there are 2 parts. One is just observation in the scanning mode, and second, when we see the central part of this region longer. You can see here very bright nearby cluster of galaxies. There are 6 clusters on this image, 1.5 cluster per square degree, and this majority of 430 objects are quasars. This quasar, very bright, is at redshift 1.08, I think. I do not see here. This is Seyfert galaxy, very nearby. Redshift is only 0.4, and this is star, just how to say, red dwarf, which is on the 130 kiloparsec from us, but corona is much, much brighter than solar corona. 430 sources on the 4 degrees, if we will, how to say, multiply to 10,000, because whole sky is 10,000 times higher, you immediately getting then on the whole sky we should detect of the order of 4 billion sources. This is one detector, but 6.7 thousandths. I think if we recompute it will be for whole Rosetta 6,000, for 7 detectors, it will be 6,000 seconds to get such thing. Yes, this is a central region. You remember it was practically invisible there. Here is longer exposure, 1 degree to 1 degree, and a lot of sources which were invisible. You immediately get in them because you have higher, longer exposure. And this is our galaxy, Norma spiral arm. And what is important that Rosetta is able to observe very bright transient. This is Maxi, but because due to pileup, image of this bright source is not, how to say, round. It's becoming very elongated, this pileup, because it's so bright. I can tell you the computation of my young colleagues. They are very interested in the tidal disruption when crazy star is deciding to go very close to supermassive black hole, and then due to simple tidal effect, in reality non-relativistic, star is disrupted, half of gas is going to infinity, half is captured, and you are getting, yes, you are getting enormously bright flare from the accretion disk. This is well known. A lot of people, Martin Rees, for example, they were working on these things. And I can tell you that estimate of Ildar-Habibulin, which are checked now with many people, we should be able to detect during 4 years several thousands of such events, which is, instead of maybe few tens, which are well known now. Yes, this is a dream of, old dream of Zen Striker. You know, these are filaments and warm hot gas. Rosetta can absorb it, and we think that we will find missing baryons and others. Yes. Now, what was the main goal? I told you already from the beginning, this was to detect all clusters of massive clusters of galaxies, observable galaxies, and observable universe. But in addition, we know we are able to create X-ray selected sample of 3 million acritic AGNs. And this is enormous because it's possible to do baryonic acoustic oscillations and many other things. This is the cluster of galaxies. I show you synergy between microwave and X-rays. This cluster was observed by Rosat spacecraft, which made first sky survey. If everything will be okay with final test of Rosetta, I can tell you that we should be 25, 30 times more sensitive than we will have than Rosat. And angular resolution is much better. And these images, and this is synergy with ALMA observations in microwave band. And Hubble observations, a lot of gravitational lenses in these clusters of galaxies. A lot of, all best instruments were observing it, but Rosetta will observe 100,000, and it will be an enormous amount of strong gravitational lenses which people can walk further. Now this is the, how to say, reclama slide of the SPT, which is great instrument, and our child is a little responsible for this instrument. And they show that after 4 years, Rosetta will lose to the microwave experiments because of sorry, but it's okay. That's myself here. Yes, but we can see here that blue is a project. What Rosetta will, what SPT will get in 3 years. From the SPT-3G with a lot of 16,000 kilometers, if I remember correctly. And these are existing clusters of galaxies, black, again SPT without Oh, thank you very much. Yes, most important now not to put it to my pocket. Yes. Oh, you see how much is better. And red is the flank, 900 clusters. And you see here that this is a competition. This sensitivity of E Rosetta, if exposition in every point will be only 1,600 seconds. If we can, in the polar regions, in the ecliptic polar regions, sensitivity will be maybe 5, 3, 4 times higher. But this is a real competition. But as you see here, up to 3 times 10 to the power 4, E Rosetta will get all clusters at any redshift. But for SPT, life is better because, how to say, in microwave clusters, brightness of the clusters and spectrum does not depend or do not depend on the redshift. Therefore, you can observe clusters easily at any redshift. Let's go further. This is well known. Just to get sigma 8, you can observe how clusters are evolving at redshift. Amount of clusters at redshift 1.4, they went to kindergarten, redshift 0.5 there at the school, and near us, you see there, they gained a lot of mass. There are many massive clusters. At redshift 1.4, amount of massive cluster is much lower. Okay, and this will permit already to do cosmology. And these are computations of Marat Gilfanov and Alex Kolodzik and MPA. You see the prediction for AGN cosmology having 3 million AGNs using coastal data with delta Z from photometric or rough spectroscopic observations. It will be 10 sigma detection of baryonic acoustic constellations. Promises really very, very promising. There was a lot of discussion in the times when still KGB was very strong, and yes, before small minimum. And you see here that we decided to divide the sky. From the beginning, we agreed that 50% will go to Germany for the creation of the instrument, and 50% to ET for the spacecraft launch and so on. Please.
I got the east now. The west now instead of the east now.
No, this galactic coordinates. I can tell you in the beginning, this region was Russian. We chose the southern sky and to work with SPT. But then directors of the small observatories in Russia, in reality 20 people came to me and told that they will write a letter to Putin because there will be Russian spacecraft without possibility for Russians to observe because this will be southern sky. After that, everybody told me, no, please change. Germans were very happy, obviously, to get southern sky with a lot of big telescopes. But this life, we have northern sky, which is, not everything is observed from the south pole. From north pole, nobody is doing well. I can tell you, we are doing now calibration and PV, performance verification phase, and Russian ideas is the following: to see the galactic reach, 200 kiloseconds. A lot of people are interested in Russia in the galactic objects, stars, white dwarfs are creating white dwarfs, neutron stars, called neutron stars, and so on. We are very interested in the Lockman hole. We were extremely interested in the very bright, very well-studied deep fields on the south. But Lockman hole is now our choice, one of our choices, and one cluster of galaxies. And during few last days, we are observing SS 433. We see beautiful shock waves where jet is interacting with the U50 envelope of old supernova. Okay, M82, everybody knows there is a fountain of gas, and Raka dark cloud to separate soft X-ray background which is coming on our side of this dark molecular cloud, and which part of the background is coming from another region, and what is the structure of molecular cloud. Now I have very short time to speak about the things which I was rather unhappy because nobody mentioned it practically during this conference, spectral distortions of CMB. And I think still that it's very important, and it's important for two reasons. There are two milestones in the history of our universe. First is last scattering surface. From this side, at lower redshifts, we see all angular fluctuations, and on the last scattering surface, practically all fluctuations which Planck observed are formed here. This redshift 1100. And there is also black body photosphere, because CMB spectrum is impossible to create here, and it can be created only at redshift 2 milliamps. There is all solution in 1970 which we got with my mentor Zeldovich, and there are two types of spectral distortion. Y-type distortions which are observed, and I was very happy to see the results from Atacama Cosmology Telescope together with Planck, beautiful Y maps now. And this is mu, post-Einstein distortions, where there is huge deficiency of the photons in the low frequency part. This is important, and why it is important, this Y distortion, I will not stay here, this Planck image of the coma cluster, I think that here is more than 100 sigma, therefore it is absolutely great. And 900 clusters were detected. Now it is Planck is giving 1,300. And I'm very grateful to Jean-Luc Puget, because for HFI, high frequency instrument, he chose filters of Planck, so that in low frequency filters there will be diminution, shadows in the direction to the cluster of galaxies, and with high frequency there will be positive signal, which Planck immediately saw. And this is mu spectrum as we thought with Zeldovich in 70, and this might be created only from redshift 10 to the power 5 to 2 times 10 to the power 6. This solution, analytical solution, which for double quantum production of soft photons is this, and we are getting 2 million using this thing. Photons which are created at low frequency are moving and feeding this deficiency. There is another effect. If, for example, we have excess of photons here, then photons are going in opposite direction, post-condensation, and are absorbed at low frequencies. Yes, this is Y and mu in comparison. You see here, this is Y, and this is mu. You can see then how they are different. And there is also intermediate. In this intermediate case, measuring the spectrum, you can find, for example, if there is decay of particles, what is the lifetime of particles, or when at which redshift the energy release is occurring. And I can tell you for which way it is important. If I will take L number, you know all L, this is the acoustic peaks, which are important up to L, now of the order of 10 to the power 4 for Atacama Cosmology Telescope and SPT. You see that we have so great sensitivity of SPT and Atacama Cosmology Telescope just due to silk dumping. If silk dumping Joe will not tell us that there is this dumping, it will be impossible to reach so high sensitivity for the clusters of galaxies. Only the physics is stronger, nevertheless. You see how strongly the fluctuation, primordial fluctuations decrease. And there are mu type fluctuations which we can observe up to L 10 to the power 8. These 5 orders of magnitude in L, if we will be able to observe spectral distortions. This is also in the K space. This is in reality from 7 to 70 folds of inflation. And this is practically very close and very close to the finish. This is a spectrum of radiation from recombination of two recombinations of helium and a recombination of hydrogen. It's possible to measure what is the abundance of helium before any star might be created. You see the spectrum, and it's question when people will be able to observe this beauty, which is in reality spectrum of hydrogen, redshifted 14 or 1300 times. Yes. Now, just this, I have additional one slide only. Experiments of the type of Cobivirus, which was Nobel Prize for the John Mather, are possible not much often than once in 25 years. And today some theorists are dreaming that it is absolutely necessary to detect new type distortions, which or from both condensation or from energy release should be on the level exceeding 10 in power minus 9, delta T over T. Such a sensitivity will permit also to study recombination lines of hydrogen and helium coming from these redshifts and a lot of details. It's very important that this spectrum will be distorted by wide distortion from the time after recombination. And Y effect, how it created between redshift 10 power 4 and 10 power 5 will be not, it will be possible to distinguish them. Yes, and I will show you again this is my last slide, that I hope that within several decades somebody will measure not only Y distortions, but also new and intermediate, which is created between last scattering surface and black body photosphere of the universe, which is also very, very important milestones. And I hear, at least in Russia and Germany, I regularly hear from physicists that CMB was created on the last scattering surface, which is completely impossible. It is just scattering. Okay, thank you very much.
Now we'll hear what experiment Roger is building.
Roger?
Thank you.
May
Oh, yes, thank you.
this important instrument.
This experiment.
Yes, it is. It's correct. I think it's. Still alive.
Well, firstly, thank you very much to the host and to John, especially who called me a couple of weeks ago and asked if I would show up for this panel, and I didn't know quite what to expect, but I really enjoyed it and had the opportunity to bring some sunshine to these dark matters in Chicago, and I've also learned a lot from the talks, and so I'm very grateful to have the opportunity to get caught up in a subject where I'm not a sort of major practitioner, but somebody who's been very happily carried things around a bit. I didn't quite know what John had in mind when he said you've got to talk about tools. So I looked it up in a dictionary, as Rocky would have done, and I got stuff about gardening. So I then went to the Urban Dictionary, and I don't quite know what this has got to do with cosmology, but it's not working. So yeah, but I thought maybe this hugely overinflated was describing the universe, and it's got rather large fringe boots, and it's a guy, of course, so I thought what I'd try to do, well, using this as a model, is deal with I suppose, a more general discussion of the issue of, what to do next and how, rather than a specific one. And so this is sort of a diagnosis, perhaps, of diagnosis, and then, of where we are now, and a prognosis of where we might be going, and then, in the spirit of this, an osteognosis, Greek root, so if I can go on to that one. So, just let me say to somebody who takes almost should take none of the credit, unlike my distinguished colleagues here, especially sort of Rashid for anticipating a lot of the microwave background, and John for executing amazing experiments. And it's been about the development of the standard model, when everyone's all bogged down in controversy, has really been a magnificent achievement. And the whole subject of cosmology has been transformed from sort of metaphysical speculation to enduring measurement. And it's been driven, by technology, but also a lot of theory and management as well, for that matter. But opening up the whole 70 octaves of the electromagnetic spectrum, and exploiting standard physics to develop the model we have right now. And it was never a given that the universe would be as basically simple. And there are books written about whether there's 5, 6, 7, or 8 numbers out there, but you could say 5 basic ones, and then the other ones describing extraneous effects. And that's extraordinary that it is that simple, and it's been described so well. There are fundamental puzzles which have undoubtedly been thrown out by this whole technique, and that obviously involves. I would say my own personal list is that dark matter is the #1 puzzle, the one that is the scientifically approachable one, and we've heard. I wasn't going to say an awful lot about it because we just heard Jonathan give us a very good. I think #2 on the list, I think, would be inflation, where again there is the opportunity of addressing these very fundamental issues. And then the third would be what I would sort of call the cosmological constant, and I'll editorialize slightly here, in that although I know it's called it dark energy, it's a very good marketing device and all the rest of it, but once the universe was accelerating, the cosmological constant, like general relativity, was a rather special explanation, sitting up there in a pedestal, ready to be knocked down by experiment, but not a big thing. It's been it's been part and parcel of cosmology since 1918 or so, and Bondley's book has flat lambda CDM. It worked out in 1952 and all of that, and so it's always been there. And the fact that it is a large part of the universe is good, but some people find it very mysterious thing. But I think if you don't have such a strongly reductionist view of what it actually is, you don't see it as an expression of the vacuum, but as something, an expression of physics on a large scale. It's something that's there, and we'll see whether or not people have been able to treat departures from this. But anyway, that was what I was going to say about that. But we're obviously at a time when this has been, in some sense, a large part of this meeting is when there are attendees out there, Hubble, S8, various other ones too. And I would say, sort of looking at this from a larger position, that this is actually quite normal at this stage of development in the science. And whether or not the resolutions are due to just a series of systematics, obviously different in different approaches, measurement, learning things about the messy business of measurement, learning about very new astrophysics, or indeed learning about new physical constituents of the universe, which of course is probably the most exciting. I would say, for me, my get as a sort of what used to be called a reluctant conservative, someone who goes for the most, what seems the most reasonable outcome, but hopes that that's wrong. This is probably the most likely, and that's the least likely, but the interest is probably the other way around. And so we'll, in some sense, some confidence that this will actually all be sorted out, and there will be a reconciliation. I would like to say a little bit about that here. In this sort of benighted age, there's a very strong temptation to polarize everything into see winners and losers, black and white, and all the rest of it. I think it's important in the way that this sort of science is portrayed publicly to say that this is a reconciliation, not a contest. And I have confidence that the Hubble constant will be determined with much more than the accuracy. Everyone will accept the answer, but in so doing, you will learn a lot about technique. You will learn probably about astrophysics. You will learn maybe about a new constituent of the universe. Who knows? But it will be learning, and it will be magnificent progress on all fronts. There will not be losers in this activity, and I think we want to be careful not to give people a different impression. Now, the standard model, just like that of particle physics, which has been gloriously successful too, has a netherland beyond it, beyond the standard model, of many big questions, and they've come up here. The nature, of course, of these fundamental elements, but we've had a lot of that at this meeting, and so I want to take a slightly different approach, and I want to say something about sort of narrative history of our universe and the galaxies, the stars, and planets, and I'll say a little bit about that if I can. So how do I yeah. Oh yes. So this is. I was going to say here. Yes. It's a good time to be doing this because this is something that's an observational hiatus. I think all this glorious progress has been in cosmology. It's a little bit of a resting point now, but we're totally confident that going forward, the new instruments that are coming online, including of course Erazit and and so on that Rashid just told us about, these ones are coming online, and they have to be another growth spurt in understanding of this. And I should say that I'm a sort of Marxist astronomer, and I belong to none of these clubs, so I'm not here as a shield for anything. And I'm not going to promote any particular mission, so I'm sorry to disappoint John about not having my own experiment, but I think we would, the future must be very bright going forward, and to be one of discovery. So, and I'd like to say this just about the business of discovery. If one looks with tongue-in-cheek a little bit, and no sort of great historical acumen, at the major discoveries, and you can make the case, and obviously I'm oversimplifying a much more rich history and so on, that most of the major discoveries, and this is just a list here, were in some sense unscripted. Just to say, nobody would ever claim that people didn't know what they were doing, but in some sense there were surprises always along the way. And these are perhaps some of the bigger ones that have been out there over the last 30 or 40 years. And obviously it's a much more complicated business. Now, you might say that the conclusion you should draw from this is that we don't know what we're doing. And that is certainly a reasonable one to make. But it's in a good sense, and I think anyone could claim that there weren't unprepared minds at the end of these discoveries. And so they were pretty rapidly followed up and so on. But it's maybe slightly harder for physicists to accept than astronomers, but the discoveries, like burglars, they break into the side window rather than walk through the front door. And this is, and understanding the interfaces with other disciplines and other fields is terribly important for making these. So that was a sort of slightly preachy point I wanted to make. The spice doesn't come in this straight line, which often people try to plan for. And this is, if you talk about a little bit about, this is what I call the central paradox of strategic planning. And this is, this was I've shown that part of this never seen before, but I was just. About 5 years ago, I just made a list contemporaneously of what I thought were interesting discoveries at that time, and they were just eclectic. They were all over the place. Other people had made a different list, but it's a pretty impressive list. And the thing now is, with 5 years' perspective, essentially all of those are durable. All of those are still with us. I mean, it's not as though everything just went away. On the contrary, they were built upon, and they've been followed by other follow-up discoveries and so on. I think one of them may be not quite right, but the others are. We're all there for the taking, and so, in some sense, we're making science plans for the 2040s and something right now, and take the long-time view of the biggest space missions and so on. So, reconciling those two is a very big challenge, and how to actually deal with it is something that these big surveys like Astro 2020 and so on are confronting, and if you've got a very clear central problem, and you know that the path forward will provide the answer, then you take it. But in many of these fields, we've heard in these presentations, we don't have that. In that case, you know, I think one would, as other people have said, one would emphasize a sort of casting your net much wider, investing more in general observatories and less in specialized experiments, for example, looking for breaking bread and finding common cause with physicists, say at the LHC, as was mentioned here, finding common cause with other astronomers. There's an awful lot of common interest in the same observing capability, and I think one of the areas in which one could say doing this is talking about neutrinos. Obviously, there's Katrina and EXO have just made announcements the last couple of weeks. Juno and Hyper-K and June are on the horizon and so on. And yet the microwave background community is not so apparent, in my view, in those communities, and should be. You know, and I think you've got to find common cause in some sense with the other physics and astronomy communities. So that was one point that I probably wanted to make. And another point that I think Joe just made it, but I think other people make it, is that you know, it's a cliche almost. It is a cliche. Multi-wavelength and messenger occult. Astronomy is here, but it's also cosmology. It's been pretty clear from recent things that the sort of actually chauvinist microwave background observer or optical survey person is not really the future. The future, in fact, is much more panchromatic and beyond the other 70 optics of the spectrum that are not electromagnetic. You know, just to give some examples of what's out there, the ultra high energy cosmic rays, 10 to the 8 times TeV energies. I mean, obviously center mass energy is a bit different, but still, this is where discoveries can happen. The high energy neutrinos, that's coming sort of online. We're not quite sure what these cosmogenic sources are. It's a bit controversial, but nonetheless, there's clearly a science coming there, and this surely is a place to make cosmological discoveries. The high energy gamma rays, Hawke is making discoveries which no one expected. CTA, as somebody just mentioned, is coming online. The ultra low energy, if I call them that, gravitons, LIGO, Virgo, LISA, constant timing array, and all of these things are all coming online, and they're all going to be part of the cosmological story. They're great tools for investigation. There's the GRBs and the FRBs. The FRBs, we may not be sure what they are, but we know that they're going to be great cosmological tools, and we can use all these things. Okay, so I think that's, did I get that right? Yeah, that's right. Sorry. So the point I'm going to make is, what I've repeated in some sense, is that there's much more to cosmology than fundamental physics. For many people here, it's the fundamental physics. It's this quest, for basic science and so on. This is a splendid thing and motivates particle physicists and all the rest of it. But, there's much more to science than that. And I would say that just describing the miserable universe that we inhabit is a wonderful thing to do. People love maps, people love making maps, and we should too. It's the sort of traditional activity of the astronomer, the second order profession and all of that. And they sitting on your back on a hillside and telling stories about the sky. It's okay. And we should not be ashamed to do that in a modern context. And in particular, the story, not just of where things are, but tell the story of galaxies. This is the Burgess Shale over here, and the fossil record and so on. This is a great popular appeal, and is a great scientific appeal too, as well as understanding what W is, or measuring the mass of neutrinos or whatever. And we're on, is a very different type of cosmology that's coming, the near field cosmology. With Gaia, that's always been there, but Gaia, I think, is going to be, personally, I think, is going to be transformational for understanding about what matters. There's a lot that we can learn from that. And it's again opening up in new frontier in some sense for research. And for many people, galaxies are sort of rather messy things, and they sort of acknowledge that, but say, we're not interested in that. We only want to just get a couple of numbers that characterize bias so we can do large-scale structure and compare with micro background and so on. But galaxies are tremendously interesting in their own right, and telling that story and understanding which came first, the black hole chicken, the galactic chicken, or the black hole egg, and things like that. All of that is a wonderful thing, and there's great astronomical, public, and I think cosmological appeal in that. And I've had one sort of message to the future is that spectroscopy is absolutely essential. You can't have too much spectroscopy. I think some of us were at a meeting a couple of weeks ago where Will Percival said that the last spectrum will be taken in 2061. I don't know whether he was terribly serious, but nonetheless, it's, you know, to get as much spectroscopy as you can will enhance cosmology in all of these fronts. So, you know, in terms of one of the big questions we have to answer, I think, is looking at galaxies which are, you know, in many branches are just, you know, treated like elementary particles as having a mass and a spin and so on, and just a few, you know, we can just sort of use them like you do in the LHC. But are they more like people? I mean, are they? Everyone is different. You know, if you look at galaxies beyond the redshift point, they're totally different from the local ones. It's another, you know, it's another country, as Sidney Vandenberg used to say, and you know, we have to confront that, and we have to understand that, and whether or not we can really average over them or not. But even if we can't, just telling their story is a very, very interesting thing to do. Okay, in that sort of spirit, of sort of mapping at least, I'll advertise one little thing that I've been quite interested in involving, is trying to make a map on the very largest scale with 2 or 3 gigaparsec resolution of the universe at large, and using these maps to do sort of non-standard tests of cosmology. This is sort of an attempt that we made of just providing this structure within a sphere and assuming sort of Gaussian conditions and so on, and sort of looking at this on the very largest scale as a sort of start towards filling in as much of the interior of the large scattering surface as we can. So I just sort of say that there, and I would say obviously this is useful because if we know there's a potential minimum over there, then that's a good prior to put in the redshift survey, for example. My final slide, and this is something that I've not seen very much represented here, although Jonathan did bring it up. But it was at this last meeting I had to go to the main meeting in Cambridge, and there it was a very large part of that. And I bring it up not so much as to having a very firm position on it, but I bring it up, and I think it's something that we really ought to be thinking about and discussing perhaps on this panel, is that, you know, simulations have become over the years a very prominent part of cosmology, and many would say a preeminent part of cosmology. We've had, you know, and rightly so. And we're now in the middle of this, what I would call the third neural net revolution, which is for real. It's, you know, people who don't know much about computing are making major advances on how they deal with data and so on. And, you know, there are validated, amazing validated speed-ups of routine tasks. There's no quarrel with any of that. No question, I think, that is a you know, thing we should be teaching everybody about, and we should be using it. And then, of course, these emulations, we sort of live in a world of their own, and the issue is internal consistency between different simulations more than it is the confrontation of the data at this point. But then there's this magical phrase, marginalize over the astrophysics, and, you know, subgrid modeling, pressure smoothing, you know, the plasmas and the radiation and so on, saying everything's just rank ordered and all of that may all turn out to be just possible and just real. But to work into old geezer mode, I really am worried that we could be getting into some terrible mistakes without giving paying due justice to the underlying physics and doing the best we can with some terribly complicated processes that are going on. And I think one of the things we have to be careful about is that all of our students don't go off to courses in computer science, which they need to have, of course, and don't pay attention to the cosmology. So I throw this out there as perhaps a topic for discussion. Thank you.
We're running late, so I want to open it up to questions quickly. But while we're on that way, I'm just looking at Jonathan and thinking, you know, when I was a graduate student, the idea of joining a collaboration with 3,000 people to do something didn't seem all that appealing. But you're saying the future of dark matter detection are a bunch of small, cheap, quick projects. It sounds like that's a change. So this drilling down in the WIMPs is big projects, but the expanding out will be 1,000 flowers blooming, and we'll.
Yeah, so I do think that's true, and I hope it's true, actually. I would just say, from our experience on Phaser, the number of Atlas refugees that come to Phaser because they purposely are tired of dealing with 5,000 people is extraordinary. And you know, it has its place. These large experiments, large colliders can't be done with a few people, and obviously they're tremendously successful. But I think we can suck more physics out of them by going to some of these smaller projects with very little investment.
Can I raise another issue which I've been clear? And that is, one of the problems is that I think most of us have a sense that there's an optimization of investment of finite funds into astronomy that goes after big things and little things and has the right balance between the two. But you know, the big stuff, by and large, is too big to fail, and then actually cuts out the small opportunistic science. And do other people share this concern, and do they see a way, you know, around it?
Anyway, we'll go with questions.
So yesterday, Risa suggested measuring every galaxy as a goal, and it seems like Roger got really close to saying the same thing. But I'd just like to ask the panel how that looks to you. You know, are there tools you would want to do that, or whatever thoughts you have?
Well, I think it's something, you know, you're looking at 1 trillion galaxies, you know, in imaging at some level. And obviously, you don't need to look at every galaxy, but you need spectroscopy is what you need,
Yeah.
I think. And I think that opens the door to so much.
So what tool?
Well, I mean, obviously, we'll see how Daisy does. And,
What's next?
well, I know some, I'm not an expert, but, well, maybe Risa's here, maybe she.
You're talking about billion.
Yeah, people are talking, there are projects out there.
Surveys with more than that dollars to do them. But 100 billion galaxy survey, that will be spectroscopic survey. That's, Risa mentioned maybe by 2060. It'll be a while.
Will Percival was the source of that number.
More questions? Simon?
I was just wondering whether people would agree that what Roger just said is actually a problem. In other words, is the concentration of people into big projects, which is definitely happening, is this actually crowding out smaller projects or not? I mean, do people actually know cases of what seemed like very promising small projects which were unable to get people or funds because of this crowding? Because in the end, I don't know. My impression is that people see something which they think is promising and doesn't cost a lot of money, their enthusiasm can usually get them the funding. So I'm not sure if this is really a problem. But I'd be interested to see what other people think.
My impression is it's not a problem if you have a good idea. If you want to do a small team and do the next CMB experiment, you've got a problem. But if you're doing new things or probing the dark matter space, I think the funding agencies are you know, they want to help, especially if there's students and postdocs involved. Rashid?
Yes. So here, yes. I wish to mention in this connection that NASA, for example, supported the project of Martin Weisskopf to measure the X-ray polarization of many sources. And it is extremely promising and small and cheap experiment in comparison with anything really big. And I think that as polarization became extremely important for CMB research, my impression that the same is the future of X-ray astronomy. Is we can understand a lot of things like neutron stars much better.
I'll give you the counter to that is that we've been waiting 40 years for X-ray polarimetry in some sense, and and this was the winner in a very large competition for the Explorer program, which is perennially underfunded. So for every Martin Weisskopf, and it's great, there's a lot more out there that is good, that are as good science that in the context of NASA are having to wait. So I think that's, this is the, compared with the cost of WST or something, that's really the dynamic balance that we're talking about here in NASA's context.
Yes, but there is additional revolution, reality revolution in the small physical labs, where people were able finally to see the recoil electrons, how they remember the polarization of incident photons. And only when this was proved in the lab, people NASA agreed to do this because sensitivity now to polarization is 100 times higher than in experiments which we dreamed 30 years ago. This is great revolution.
Joe.
So here's a counterexample. An experiment was designed to improve on FIRAS by 4 orders of magnitude. And it was not expensive by the standards we're talking about. It got turned down twice. So again, it's not clear that there is a space for what would be major contribution by.
Yes, just to see the old spectral distortions and this very promising field also.
Maybe I could just comment. I know that particle physics may be in a different stage than astrophysics, so this is slightly different. But I do remember a couple of years ago, Raphael Lang, who's a fantastic dark matter experimentalist, noted to me that his experiment, something he was proposing, could be funded for the cost of an Atlas collaboration meeting. Just the travel costs for 3,000 people or whatever to go somewhere. So I think clearly there's a role for big experiments. The thing is that the funding should mirror the scientific thinking at the time. There's always a lag, right? If you know you're going to get the Higgs boson, yeah, you should go get it, and you should form whatever collaboration it takes to get that, because that's the prize. But at this point, we're, at least on the particle physics side of things, quite lost. We don't know which way to go. And we should not continue to operate in the Higgs mode way of doing things. We should now fritter away into smaller groups and try to probe a number of different things. And reducing that lag time, I think, is what we should
I might just remind people that there are small groups that are doing all-sky surveys with a CCD camera and a CCD detector and a Nikon camera. So it is happening, and it can.
And measuring the spectrum of the early universe with a single radio telescope is happening,
Well, I tend to agree that, in fact, with that, with these big experiments, and so there is a difficulty for smaller groups, for example, to get funding. And in fact, this also brings something to my mind. Like 20 years ago, when we had a meeting about cosmic acceleration here, and the opening talk at the end said, we have no idea, as theorists, what's going on, so go as observer and experimentalist and get us some clues from observation for cosmic acceleration. That was Ed Witten when he gave his opening talk. So I personally find it, so now 20 years later, we heard Andy and I think another person in the panel saying the opposite, saying that we should encourage today theory to come up with new ideas for cosmic acceleration. So my observation in the last 20 years that is, I think there was less opening towards new ideas, for example, towards cosmic acceleration, so there was more focus on some kind of one single idea or something, where other small ideas were not necessarily encouraged. That's my observation.
Any other questions? We're actually at the end of the time period. Well, I think before we thank the panel, I mean, the tools we have, I think Roger spelled it out. What's coming down the pike is absolutely amazing. What we have now, I know a lot of the groups have a hard time even keeping up with that data. So we don't have to worry about employment. But it should be very exciting, and I just hope that this message, that we need to be multi-messenger in the sense that we all work together, that we encourage the astrophysics, that we go back and forth. I think that's what it's going to take to really crack this nut. Anyway, let's thank our panelists one last time.
Well, actually, I learned quite a bit well, partly my job, I think you and there are people who are really know what other people are saying. So that's what
Team A, Team B.
So I think it's
processing.